Hello, everyone. In this video, we are going to look at the graph transformation vertical stretch. So a vertical stretch of a graph is as if we've held on to our graph from the top and bottom and then just pulled vertically. We also see that this type of transformation gives us vertical compressions. So that's if we did the same movement, held on to our graph from the top and bottom, and then just smushed the graph down. So to build some intuition here, that's if we had our graph, and if we are vertically stretching our graph, we just pull it up like this while fixing our axes. If we changed our axes as well, then we really wouldn't be changing the graph. But if our axes are fixed and our graph we just stretch like this, that's a vertical stretch. Or if we smush our graph like this, that's considered a vertical compression. So this type of transformation is what we are going to look at in this video. So in order to help us determine what operations we're going to use in order to create such a transformation, let's look at the first example. So this example says complete the table using the function values for g, what happens to the graph in each case, and then sketch and label the graph of y equals 2 times g of x and the graph of y equals 1/2 times g of x. So similar to our vertical shift video, we have a table of function values here for g. So let's first fill in the next row of function values for 2 times g. So what we're going to do is take the output value of our original g function and then just multiply by 2. So our first cell will have 2 times -2, which is -4. Our next cell for 2 times g of 0 is, well, we have 2 times the output, 6. So 2 times 6 is 12. Next up, 6 again. 6 times 2 is also 12. 0 times 2 is 0. -2 times 2 is -4. So now let's take a look at what the graph of 2 times g of x would be, just using these points that we just found for 2 times g. So at -2, we were down here at -2, but now we're going to shift down 2 more to -4. At 0, we were at 6, and now we're going to move up to 12. At the next 6, we're still at 12. At 0, we are again at 0. And at at 8, we are at an output value of -4. So now we can use our ruler and connect our dots here. Now let's take a look at the next example. So now we're going to take the output values of g and multiply by 1/2. So our original output, g of -2 is -2. So when we multiply by 1/2, we just get -1. Then we can continue filling in this row. So g of 0 is 6 times 1/2 is 6 times 1/2 is 3. And then we can continue. 6 times 1/2 is 3. 0 times 1/2 is 0. -2 times 1/2 is -1. So now let's, on the next set of axes, plot the function 1/2 times g of x. So when my input is x equals -2, my output would be -1. When x is 0, my output is 3. When x is 4, my output is again 3. And here I'm just reading inputs here, outputs here. So when input is 7, I had 0, I again get 0. And when my input is 8, I get -1. So now we can connect our dots to form our graph. And now let's go ahead and take a look at what the behavior is for each of these transformations. So here I have 2 times g of x. And so what we can observe here is our original output values. So at 0, say, we were originally at 6. The transformed graph 2 times g of x stretches this 6 out to be twice as long. So that's where we see that multiplication by 2 happening. And similarly on the negative direction. So if we were originally at 2, then we're going to stretch to be twice as long. So that's why we're seeing this type of stretching happening. Something else that we can observe is wherever our original graph was 0, our stretch graph is also 0. That's because if you stretch to 0, then you're still going to get at that same place, 0, no matter what you multiply by. So in that sense, our graph is scaling, being scaled, both in the upward and downward direction. Again, we can think of that image of just pulling our graph from top and bottom and just pulling out and stretching. And now notice this other transformation is similar, but in this case, when we're multiplying by a fraction that's less than 1, our graph actually gets smushed. So originally we had at x equals 0, we had 6, but then our transformed graph is down here at 3. So all of the numbers that we originally had are now scaled by a factor of 1/2. So if we were down here at -2, then we get smushed to just -1. So again, that image of holding our graph from both directions and then pressing inward to smush. All right, so let's look at a summary of what happens with these vertical stretches and compressions. So if we start with a graph, y equals f of x, then the graph y equals a, which is some constant, times f of x, so multiplying f of x by a, is the transformation of our original graph f of x. And if a is bigger than 1, so that's the absolute value of a. So it might be the case that a is negative, in which case we're still going to be stretching our graph out. On the next page, we're going to look at what it means for that a to be negative. But the important point here is if the absolute value of a is bigger than 1, then the graph of the original function stretches vertically by a factor of those a units. While if the absolute value of a is a fraction less than 1, meaning if it's a number between 1 and 1/2, then the graph of the original function compresses vertically by a factor of those a units. And this we can also see if we just multiplied a whole number, say our test number is 6, by a number that's larger than 1, so like in our previous example, 2, that number gets larger, 12. But if we started with our original number 6, and we multiplied by a fraction that's less than 1, say 1/3, then that's equivalent to saying 6 divided by 3. So our number gets smaller. Okay, so let's look at an example now when a is negative. So we have the graph, or what we want to do is graph negative g of x. So this is the same as if we had -1 times g of x. So let's notice what occurs when a is negative. So to do that, let's go ahead and plot the graph negative g of x. So what's going to happen to all of my output values? So I start with g of x here, like we saw in the table. So what's going to happen is, if we look at the table, well, all of the original g values, I'm going to multiply by -1. Oops. So I am going to go ahead and just write those out here. So negative g of x would be -2. What was starting with -2, so it's going to be +2. If I negate 6, I'm going to get -6. If I negate 6, I'm going to get -6. If I negate 0, I'm still going to be at 0. Then if I negate -2, well, I'm already at a negative, so I'm going to get +2. So graphically, what does that look like? Well, if I start with -2, negating that value is going to bring that number up here to +2. Similar for this -2 here, At 0, well, the negative of 0 is just 0. What about at 6? What's going to happen? It's going to become negative 6. So I'll be down here. At this 6, we're also going to negate to negative 6. 0 will have 0. Negative 2 is going to become positive 2. Negative 2 is going to become positive 2. So if I draw my graph here, the trace of my graph, I'm going to get a graph that looks like this. So here is my graph negative g of x. So what I'd like you to do is pause the video and write out a summary of what happens to our graph when we multiply our graph or our outputs of our function by -1 or by a negative. All right, when you're ready, let's talk about it together. So what you might have noticed is that when we negate our function and look at the graph, what we're essentially doing is rotating our graph about the horizontal axis. In other words, we're just reflecting our graph along the horizontal axis. So let's write that out. So I'll say when a is negative, our graph is reflected across the horizontal, in other words, x axis. In particular, all of the y values become negated. So if they were positive, they go to negative, and if they were negative, they go to positive. So let's look at the next page at some examples to get more familiar with this type of transformation. So first, we're going to start with a graph of g of x given here. And then we're going to carry out the following transformation. So first, we're going to look at the graph 3 times g of x. So what I want to do is just start with the graph, and from the graph, see if we can determine where the output value should be. So if we start here at the output value of 0, well, the output will again be 0. Here, when the input is 0, our output is 1, 2, 3, 4, 5, 6, -6. So if we're down here at -6, and then I multiply by 3, where will this value go? Well, -6 times 3, that will become -18. So where I'm going to place my output value, 3 times g of x, is going to have to be all the way down at -18. So we want to keep that in mind when we're labeling the axes for the graph of 3 times g of x. So let's go ahead and label our axes by 2's. So I'm going to label this 2, 4, and I'm going negative direction here. So negative, -6, -8, -10, -12, -14, -16, -18. So this way I'll be able to make sure I have enough room to plot my output values. And now pause the video and fill in the horizontal axes as well. So to draw our graph 3 times g of x, I'm just going to take every original output value of g and multiply it by 3. So we're starting at -6. So I'm starting here at 0, because 0 times 3 is 0. Then when my input value is 0, we already determined that I'm going to get -6 times 3, which will be down here at 18. I can find another point here when my original value of the graph input is 3, output is going to be 3. So let's plot that point 3, 3. And here I'll have 6, 3. So my next point, my output value is 3. Oops, and that's a negative. Good catch, everyone. So I'm going to multiply -3 by 3. So I'm going to get 9. So my input is 3. My output is going to be -9. And then when I'm here at 6, my output value is again going to be 9. And again, -9. So that looks like this. So then to draw my graph, I have this circle here that's been stretched. And I go up here to my next point with a straight line and over. So we can see that what's happened to my graph is that this original circle just gets stretched out. It's as if I just pulled my graph down like this and up, but there's no positive value, so we don't really see that stretching on the positive side. So now let's take a look at our graph when we multiply by 1/3. That is, we multiply our function g of x by 1/3. So similarly to the problem that we just did, we can see that when our value, or when our input value is over here and our output is 0, again, our output of 1/3 times 0 will be 0. So in this case, I'm going to label my graph with just a unit for each square. So I'll say this is going to be 2, 4, 6, -2, -4, -6, 2, 4, -2, -4, etc. So over here at 6, I'm going to have 0 again. Then when my input is 0, my output was -6 before. So I'm going to have -6 times 1/3, or 1/3 times -1/6, which is going to be -2. So now my graph smushes here, or compresses to -2. And similarly, my original output was -3 and -3 along this line. -3 times 1/3 is just going to be -1. So now at an input of 3, my output will be -1. And similarly at 6, my output will be -1. So my graph then will have our circle that's been smushed there, and we'll have our straight line connecting to -1, and then over to input of 6, output -1. All right, so now let's take a look at this final example. So now what we're looking at is the graph 2 times g of x plus 3. So to carry out this transformation, we need to take 2 steps. First, we need to multiply our function by 2. Then we're going to add 3. And notice we carry out the transformations in this order because this is similar how we would carry out the operation if we were finding that output value. Similar to using those order of operations. First, we're going to multiply, and then we're going to add. So first, let's see what that would look like if we just multiply our function by 2. So similar to what we've seen before, we're going to label our axes. So I'm just going to label by 2's here. 2, 4, 6, -2, -4, -6, -2, -4, -6, 2, 4, 6. So again, that point, -6, 0 remains. But when x is 0, my output originally was -6. So I'm going to multiply by 2 to get -12. So I'm down here at -6, 8, 10, 12. And then at 3, originally I had -3 as the output. So times 2 would give me -6. Then at 6, I'm also at -6. So just the graph of the function 2 times g of x would look like the following. And I'll label that here for us. So that is the graph 2 times g of x. But now, next up, I'm going to add 3 to my function. So adding 3 here just corresponds to shifting every point on my graph up 3 units. So it was 0 will be 1, 2, 3. What was down here at this -12 is just going to go up to -11, -10, -9. What was at -6 will go up to -3. And similar for that last point. So when I shift my entire graph up, I'll have the same shape, but now all my points just shift up. So I'm going to label this graph 2 times g of x plus 3. All right, great work, everyone. Feel free to rewatch any parts of this video to help this material become more familiar, and then continue with the questions for these video assignments. Great job.